guys. Welcome back. Made it through a week. So when we left off, we were trying to break Netflix a little bit. I'll repeat my disclaimer, especially since this will be on the internet forever. We're probably violating some terms of service with Netflix. As with any time you add an extension or mess with the front end of any website, you're most likely, probably a safe assumption that you're breaking some terms of service. But what I want to show, why I want to show this stuff is to show that this is technically possible. And when we're building our own websites, I want to stress that we cannot trust our end users. Just because we have an end user agreement out there doesn't mean everybody's going to follow it. And this is a way that people could potentially hack into our back end of our servers and really start breaking things. For example, if you have a drop-down box with two options, and on your server, you're just checking, you know it's going to be one of those two options. I know they can only submit those two options, so you don't have your extra checks to check for third and fourth and any other option. Well, somebody's just going to add a third option to your drop-down box and then submit that, or send the request directly. So the point I would need to make here, that I'm making here, people can mess with your HTML, your CSS, your JavaScript. That it will not always be just whatever you send them. They can modify that at their will. So let's modify Netflix at our will. So we had our manifest for breaking our own site, and I just said anytime I'm opening a file, just run this thing. Let's get a little better with this one. And let's say whenever we're connecting to Netflix.com, and specifically browse, we don't need to run this when we're watching something, so we'll just look at the browse path. So whenever I'm browsing that main screen, choosing something to watch, I want this code to run. Specifically, I'm going to run netflix.js, a file I just created here, and now let's start thinking about what we want to do here. What JavaScript do we want to run whenever we go to Netflix's browse page? So let's check it out, and they're still running this killer stuff. I don't want this to be on there, but we'll take what we get. So let's check out the HTML here. And if you're building extensions, a lot of it is going through the HTML and the JavaScript, CSS we don't care as much about, to figure out how a site is structured so you can start manipulating that and making changes that you want to make. So let's find out what element this is that's auto-playing these things, and I have it in my clipboard just so I don't have to look around. It's this volatile billboard animations container. If I right-click this and delete it, that's gone. So I'd like that to happen each time I load the page. So let's try to find that element and delete it with JavaScript. So if I refresh this, let's take a look at the structure of that element. Page didn't load yet. So we only have one thing to work with. Unfortunately, we don't have an ID. That's the easiest way to work with this stuff. Just get the element by ID. You know you have that ID. You know it's unique. You have that exact element we're looking for. Here, we don't have quite that luxury, but we do have a class name, and we know this is a span. That's what we can work with. We can get each element by type. We can get every span and look for this, or we can get every element with that class name. Now, I'm looking at my search. I can see there's only one element with that class name. So let's just remove every element with that class name. And then that should get us where we want to go. So let's go to our JavaScript. Let's just have a little message here. This, you wouldn't normally do this, unless you want to. You can normally do this. But I just want to show that this is running like we did on Friday. I just want to show that the extension is running when it's supposed to. So let's just get a very minimal extension loaded, and then we can start building some functionality into it. So I'm going to go to my extensions, load unpacked, how we're doing it in Opera. Again, this will be different for each browser. Just Google, how do I install an extension that I'm developing in whatever browser. It'll come up with all kinds of tutorials. I also added a link to the schedule with a good tutorial. So let's go to this Netflix extension. I want to add this directory. Oops. Let me make one quick change here. I accidentally have it called AutoVoter still. I don't know, Netflix extension. If I can spell. Screw it. Netflix. Reload that so it's named properly, because that was bugging me. Let's run this, reload the page, go to our console, and we should see, once the page is fully loaded, once this stops spinning, we should see our console.log. And we didn't, so we get the debug already. All right, and I can see my error already. So first thing I double check is the URL, which is what I messed up. I didn't have the www here. Got to have the exact URL or else the extension's not going to run. So I didn't have www. Let's make that change, reload. Run this, wait for Netflix to load, then we should see our console.log this time. And that used to be something I didn't like about live coding in lecture, that, well, you're going to make mistakes, things are going to go wrong. But it's actually something I tend to like because it's more realistic. In lecture, if I just have my slides and my pre-canned examples, it makes it look like the professor is just magic and just knows everything. We make mistakes all the time, just so you know. Everybody, even the most senior developers out there in industry for 50 years, well, not 50 years, but 30 years out there, they're still making mistakes, they're still Googling things. It's just part of the industry. There's so much stuff to know. Mistakes happen. So anyway, we got our thing running. We got our extension running when we go to Netflix. And when we go, as we already saw, it's going to show it, but I already accidentally showed it. If we go to any other URL that doesn't match that pattern, we're on other sites, this extension will not run on other sites. It's only going to run on Netflix/browse. It's not going to work on Netflix/watch when we're actually watching something, just on that browse page. So now, oops. Now I lost my, I have to cheat a little bit because I don't feel like looking this up again. So we want to get elements by that class name. So I want to get every element with this class name. And then I want to work with those elements. And what do I want to do with those? For element of these elements, I want to delete that element. Now we can't just say element.delete. It's in a close paren. We can't just say element.delete, but we can do a little trick. If we go lm.parent remove. Ooh, do I have this right? No. I'm going to have to look at my cheat sheet again here. Remove parent node, remove child. Okay. Autocomplete failed me on that one. So parent node, remove child. So I'm going to go to this element's parent element. So the DOM is a big tree structure. Every element in a tree has a parent, just like 250 material there. I'm going to go to that node that I have, this element with this class name, go to its parent node, and just remove that child, which will remove that entire subtree. All of those elements contained within this span that I'm getting. All of that's going to be removed. It's just completely removed from the DOM. That document object model, that whole part of the tree, that whole subtree, gone. So if I run this code, this should be enough to get rid of that automatically. So let's get this down a little bit, reload. Our extension will run after everything loads, and we should, bam, get rid of that. So now every time I load Netflix, it's automatically gone. There is one issue with this.
I never have told anybody anything except
Still
right
have
now.
audio,
I did the most
which
horrible
is
thing we could do is take
just a little bit
somebody's life.
annoying. Now, the way Netflix, the way this page works is as soon as you start scrolling down,
I was charged.
The autoplay stops, the audio stops. Now we still get the audio, that audio trigger still went. Even though we removed the element containing the video, that audio is still playing. So let's add a little more to this app to get rid of that audio. Which is which I'm just going to simulate a mouse scroll. So if I take this, go into my console here, scroll, why is not a function? All right, just as I was mentioning earlier, we don't have scroll by 0, 10. Don't have everything memorized there. There's way too much stuff in this industry to memorize everything. But luckily we have the whole entirety of the internet to help us out, to help us remember things. Scroll by 0 in the X direction and 1,000, I believe it's pixels is the unit, pixels in the Y direction. So if I do this, I can actually scroll the page through JavaScript. This is something you could put in your JavaScript if you wanted to take control away from the user. Not recommended for user experience, but you can automate those scrolls. You can scroll down the page like I just did here. We're going to do that in our app, or our extension. Why wouldn't scroll Y work? It seems like that one would work. And I just want to scroll some minimal amount, just enough to trigger the scroll down event in Netflix to get the audio to cut off. So now that I have this, I don't need to do that. Reload the page. Takes a while for Netflix to load, so I still will get, oh, I've scrolled down already. So I still will see it, this page splash, but as soon as it's done loading, it goes away. It'll scroll down by a minimal amount, and now I have no audio. That 10 pixels wasn't really enough. I didn't even notice that scroll. I thought I would see it, but it was enough to trick Netflix into thinking that I'm starting to scroll down the page, so it cuts off that audio and stops that from playing. So now with my extension, I have no annoying auto-playing video, effectively ad, blasting me in the face as soon as I go to Netflix every single time. I generated the habit of, as soon as Netflix loads, just automatically scroll down to get rid of it. Now I don't have to do that, I don't have to bother. Then, I won't go through the rest, but just a little bit more that I added is the big rows where there's effectively an ad as you start scrolling down. I want to get rid of those. And also, running this every second and throwing these in functions to be able to, well, I'll just show you. Like, we got rid of that, but if we click one of these tabs, we're not reloading the page, so our extension is not reloading, but we're going to get another one of these. So if you run that every second, it's kind of a hacky way of doing it, but it'll keep getting rid of those even after the page loads. Question?
If it can't find the class that you search for, does it stop executing JavaScript?
So this, let me get out of my backup one. So if it doesn't find this class, this get elements by class name is going to return an empty data structure. So my loop just won't execute.
Will it execute the Windows scroll by?
Yes. So it will execute the Windows scroll by. So it'll execute just in line with the script. The for, if say I misspelled this, the for loop wouldn't run at all, and it would still run the scroll by. Which actually I could probably get rid of this. If I scroll enough, I could just scroll down past this to another way we approach this.
Is there any permission system for which websites can use which websites? I know like in Chrome, it'll say this extension can edit these web pages or all web pages or.
Mm-hmm.
It seems like they would have access to all sensitive information.
They do have access to everything. So see, this has, well, my mistake I had there, and then this one. That's just reading off the manifest, saying which sites to run these off of. There shouldn't be any security concerns because the developers of apps should be aware of the point I'm making is any HTML, CSS, JavaScript you send the user can't be trusted. If they're developing their websites and web apps properly, they're understanding that all of that is already compromised, so it can all be accessed. There are not should not be security issues unless the developers accidentally or intentionally, I don't know why they would, introduce bugs in their app itself.
I'm not talking about server-side security, I'm talking about data security. Like if you go to your bank's website, you have your account number, routing number, other stuff, all in text.
So if you downloaded somebody's extension, installed it on your browser,
Yeah,
you do have to trust that extension developer. Is that what you're getting at?
that's what I mean.
You do have to trust that extension developer, yes. So you do have to be careful, just like you are installing effectively software on your machine, well, not quite that extent, but you do have to trust the extension authors. Don't go finding some extension that 5 people have downloaded and, oh yeah, this sounds neat, downloading it. You can, but know the risks. If that's running on your, like you said, your bank's website, yeah, they can grab your password, username and password. Any site that's running, any extension that's running on any site, one of the simplest things they can do is grab your username and password. That's all plain text. They can grab that. Data. Now, obviously, they have your username and password. They don't need to go through the extension anymore. They're just going to go log in as you and do whatever they want. That's something we'll talk about, of course, at length later in the semester. But just real quick, since I mentioned it, passwords always stored as hashes in the database. If you get somebody's password, it's just a hash. You shouldn't be able to recover the password unless it's a weak password. But on the front end, in the HTML and the JavaScript, that password is always plain text. It's plain text. If somebody has access to your front end, they have access to your plain text password. It's not hashed until it gets to the server. So you do have to be cautious of that. Those extensions will have access to your plain text password. If in the worst case for an attacker, they're just going to log all your key events and then know when you're typing in the password. Okay, the password field is focused and they're pecking on the keyboard. Well, that's probably their password. No matter what, they can always grab it at that point. But in that network traffic, that password is being sent in plain text. So something to be cautious about, another thing to be cautious about in the front end. And the short story for that is, well, everything on the front end can already be compromised. What's the point of doing any hashing on the front end? They're just going to compromise the hash function at that point. Yes?
So I know you talked about how the elements have like a tree-like structure, and so for that reason you have to go to the parent to delete the child. But I still am not quite sure why you can't just directly delete like an element from like the web page. Like that seems like that'd be a really convenient function.
It does. I mean, I don't have a solid answer for you. It just doesn't exist. That functionality doesn't exist. You can do something like this element.inner.html equals empty string, and then you can start removing the classes. You can really destroy everything about it, but you can't just say delete this entirely. My guess, just spitballing here, but my guess is that then there would be a null reference in the tree. You'd have an element, a parent with a null child, and I would assume that would just wreck everything. That would mess things up. But if you remove that entire reference, then they let us do it that way. Move with that. Any last questions on this?
Yeah.
Yeah.
Is there any better way to check the, in a single page? I don't know if Netflix is one of the single page websites, but is there a better way to check if you changed like tabs or whatever, like change the TV shows than just
Yes, but it would take a bit of work on each website to really figure out what happens. So JavaScript in the front end is event-based. There are events being triggered, and then JavaScript will react to those events. So you can plug into the exact change tab event, whatever it is in Netflix, and then work with it that way, plug right into that event and be able to do that immediately. I just did the hacky thing just to get the example out there, because I didn't feel like digging into Netflix code that much to do it. I did, you know what I was trying to do? I was trying to get another example where when you hover over a show to watch, it goes big, it moves around the whole page, it starts autoplaying. I think that's annoying. So I was trying to get rid of that, and then I sunk like an hour into it and didn't get it fully working, and then I just gave up. So you can, but it's a time investment. And I need to get like slides and homeworks out, so I had to move on. But yeah, there are better ways than set interval. Yes, talk about this now. Yeah, we gotta move away from the front end. So we could spend a while looking at different sites and things. We got to move into the core of this course. So I want to make sure, I was trying to be very clear on day one, I'm going to be very clear again now, well, you still have this one last stage to add drop, just in case you're making that decision. Just want to be clear that what we've done so far is not a reflection of how this course is going to go. We're going to start getting very much more technical, more into code as we move to the server side. We're not going to do a lot of front end. What we saw here was most of the front end that we're going to do. Suffice to know that HTML works on elements and properties, or elements and attributes. CSS can be applied to that, and then JavaScript can run in the browser. We'll play with some more JavaScript, but we're not going to play with a lot more HTML and CSS. In the front end, we're not going to be designing more pages. I'm not going to say, this is an unordered list, let's use this. That's not what the course is at all. I was pretty clear about that on day one, but I just want to reiterate just to make sure, in case some of you are trying to still decide if you want to stay with us or not. Where we're going to go from here is the server-side code. So when we have a server sitting on the internet listening for requests, how does that get HTTP requests and then serve those requests back? Homework 2 is getting right to that. This is where all those rules in the syllabus and that we talked about on day one apply. No HTTP libraries, and no frameworks, no web frameworks. Nothing that completes the assignment for you effectively or makes it significantly easier. So for example, you can, for what we're doing here is just a very simple web server. You can very easily pull in any web framework and just say, on this path, serve this message. On this path, redirect, else 404, which is the entire assignment. It'd be very easy to do that with a framework. I want to peel back the framework and see how to build this thing from scratch. So with that, we're going to start with a TCP socket server. As I mentioned, you can use a TCP socket server library if it's built into your language of choice. Use that one. If there's not a common one, if the industry standard for your language is to use an external library, there was chat about C++. If you're using C++, Boost is pretty standard. You can use Boost, that's fine. If you're using Scala, like we do in 116, like I'll do for the examples, at least for today, probably quite a bit throughout the course, just because that's what we're using in the curriculum now. If you're using Scala, the akka library is standard for Scala. That's just what you use for TCP. You can use the Java libraries for it, but akka is more of this industry standard. That's what you tend to use. So things like that, but only to set up the TCP socket server for you if the library is doing any HTTP at all. If the library even knows about HTTP and you're using those HTTP methods, that's not allowed. So just want to reiterate that again. When I ran this over the summer, I said that a whole bunch of times, and then like 80% of the homework submissions used HTTP libraries. So I don't think I got my point across enough. So I want to make sure any HTTP libraries, if you're not manually parsing HTTP for this homework, you're wrong. You imported a library that's not allowed. So anyway, start a TCP socket server. This is what we'll go through today. Listen for HTTP requests on that TCP socket server and serve up just a basic hello world message of your choice on some path. So your site / something, serve up some just hello welcome message or whatever, just a hello world. One, redirect. Another path that's going to redirect to your main path. And then a 404 if it's not one of those two paths, return 404. So we'll talk about the HTTP stuff on Wednesday and Friday. Today I want to talk about objective 1, how to get a TCP socket server running and what that even means and some background on that. So Wednesday will be our first more technical lecture as we get into HTTP proper. Today's going to be more background. And these slides are posted if you want to check them out on your own. So TCP/IP, let's talk about the background that we're assuming. I'm letting you use these TCP socket servers. We're going to take TCP and IP for granted, but let's just look at some of the background of, on a very high level, what this is doing and really what the internet is. We're going to use the internet, of course, quite a bit. What is the internet? So the high level, just one-liner, it's a network of networks, that's the internet. So what are networks and what are some different types of networks? So let me just go through a few different types. A LAN, a local area network, is what we're used to having in our houses, or what we have at UB. We have all this hardware connecting one organization or one household, and there's hardware that we're familiar with, routers, wireless access points, modems. This is where we have Wi-Fi often, and I don't know if we have in this room, probably somewhere, but this room's big enough it should have one, but a wireless access point, you'll see them all around campus to support the Wi-Fi on campus. So LAN is just one network. It is a full network. It behaves just like the internet. It just doesn't have too many devices connected to it, typically. Next up from that is our ISPs. This is what's connecting those LANs together in a regional sense. So ISPs are going to connect an entire region or an entire city and connect all those machines together. ISPs solve what's called the last mile problem. How do we get that cord running right to somebody's house? How do we connect somebody's house to the internet? So ISP, you're going to call them up and say, I want some internet, and they send an actual person out to your house and wire up your house, and then put either a modem or a router, usually a modem, and whatever. They put the hardware in there to be able to connect to their network, and their network is running either in the utility poles or underground. They have those wires, those cables connecting all these houses together, all this city at the city and region level. But they're the ones who send actual people out to do the work to wire up every single house. Same concept as a LAN, just at a larger scale. So you could build a LAN and run wires to all your neighbors' houses and build out your own ISP, just a bunch of cables connecting everybody. Tier 1 networks on that next layer, this is what connects the ISPs together. So an ISP is working at a regional level. You have all these ISPs all over the globe. But what if I have Verizon and I want to connect to somebody with Comcast over somewhere else in the country? The tier 1 networks are going to connect to those two ISPs together. So these tier 1s, these are going to connect cities. These are going to connect entire cities together to form entire countries or entire continental connections. And these all have peer agreements with each other, where every tier 1 network of sufficient scale, they'll negotiate with each other, and they have peer agreements, which means they can use each other's networks free of charge. So they could bill each other and track all this traffic and everything. They say, you know what, let's just call it a wash and just say, we're all one big network, let's just all use each other's networks, because I'm going to charge you, you're going to charge me, we just have all these transactions on this overhead, it's going to be crazy. So they have peer agreements. With these peer agreements, this is what effectively forms the backbone, what we call the backbone of the internet, this clump of tier 1 networks, all sharing each other's networks. If anything is the internet, I would say that is the internet, this clump of tier 1 networks all, with all these peer agreements with each other. That effectively is the internet, and then the ISP connects us to the tier 1 networks, and then our LAN connects, gets our Wi-Fi and our houses connected, so we can connect to these tier 1 networks. You may have heard of some of these, but a lot of these, unless you've looked into it, you probably haven't heard of. But these companies are responsible for routing a lot of our internet traffic, especially L3, level 3 communications. They're, I believe, the biggest, and they just had a merger, I forget, I didn't follow the whole story, but they're at least one of, if not the largest tier 1 network in the United States at least. But there's one problem with these pictures I'm showing. Internet exchange first. So we have these massive networks. These networks have to be plugged into each other if they're going to have these peer agreements, if the ISPs are going to pay the tier 1s for internet access. These networks have to be connected, and they have to be physically connected. Not necessarily have to, but for performance, they're not using Wi-Fi. The only time we use Wi-Fi is this last little bit of connecting our laptop to a local network. That's the only time wireless is introduced in the internet. Everything else is hardwired. So connecting two tier 1s together, or an ISP and a tier 1 together, we have these internet exchanges, which are building level routing mechanisms, I guess. I don't know what the best word for that is, but buildings just filled with wires to connect these massive networks together. This one is in New York City, to connect the networks for New York City, to be able to have all this, this traffic routed to the correct networks. Oh, and so there's one big problem with what I'm showing you here. These are all maps of the United States, and these are American tier 1 networks. But we know that we can connect people around the globe. We can have global connections. There are tier 1 networks and on other continents and other countries to connect the entire world through the internet. So how do we cross the oceans? We actually have huge cables that literally plug in continents. So to get the global scale of the internet, there are actual physical cables in the oceans to be able to cross these oceans and connect continents. There's no satellites involved, no wireless technology here. It's literal physical connections. So from the whatever Wi-Fi, whatever wireless access point we're connected to, you could follow a physical wire or cable, fiber, copper, whatever it is. You could follow a physical thing from that wireless access point all the way to Beijing on the other side of the planet. There's a physical connection, and then it's going to travel all the way across the planet, and then that last little bit, somebody in Beijing probably has a laptop and has a little bit of wireless going from their wireless access point to their laptop. Everything else is very physical. The internet is a very, very physical thing. We just don't see the physicalness because the only part that we would see, we don't really use Ethernet anymore, we have Wi-Fi, and we just don't get to see how physical the internet really is. But literally, as a species, we've wrapped the entire globe in cables, and that's how we internet. That's how we use the internet. It's physical cables the whole way. And then our apps that we want to connect to, we have these large data centers, just huge buildings filled with servers, rack after rack after rack of servers to be able to run our favorite apps. There's a lot of computing power needed here. Think about how much power it would take to run Netflix or YouTube. How much storage does YouTube need with how many videos are being uploaded constantly? All that runs on hardware very similar to what's running in our laptops right now. They just have a lot of hardware. So they have tons of hardware, and then they plug in. They're going to plug in directly to a tier 1 network. Just like UB doesn't mess around with ISPs, they're going to plug directly into tier 1. So they have large cables going in here to be able to get the HTTP requests, process them, and then send the responses. So what we want to focus on in this class is what's happening in this data center. What software do we write to be able to run that center? And of course, we won't get into the distributed topics, but there are a lot of distributed concerns here. I recommend distributed systems for that, of course. Would be the course to take. To be able to run one app on this many machines, and each machine having multiple cores, how do you distribute your app to be able to take advantage of this? When you have an app that's too large to fit on one machine, it just can't possibly, one machine cannot possibly run Netflix. So how do we scale our software to be able to run and take advantage of all this hardware, but still just run one app or one service rather? The service could be multiple apps. But how do we run one service? How do we run Netflix across all these machines? And some companies, Google included, the map is Google here, they don't want to pay the tier 1s too much. They use a lot of bandwidth. So they've actually ran their own their own cables across the oceans. Google has, if you watch YouTube, I'm sure the vast majority, if not all of you, watch YouTube. But when you watch YouTube, you notice you really don't have a lot of, as long as your network is fine, as long as UB's Wi-Fi is working and things like that, you really don't get much buffering or lag. You don't get much of that these days anyway. You used to a bit more than you do now. But if you go to another video streaming site or you're watching video on some other site, you'll still experience that buffering. You still get that lag that was very prevalent back in the day. One big reason why Google doesn't have that anymore is they've spent billions of dollars, they've invested billions in their own network so they can get rid of that latency. They have data centers all over the world. They have huge amounts of infrastructure connecting those data centers, and they even have their own transatlantic cables, and transoceanic cables to cross these oceans, so they don't have to rely on a tier one. So if tier one wants to slow them down or do whatever, they're fairly immune to that. The only thing that Google really has to worry about much anymore is those ISPs. The ISPs can still play around with that. They're trying to get into more and more cities with the Google fiber. And it's legal battles and things. I don't want to go down that road. But this is why Google can serve YouTube with such low latency. It's because they're really independent and they just built out their network so much. They've invested so much money into that network. As you can imagine, these cables crossing these oceans are not cheap. These ones, the green ones. Okay, but how do we use these cables? Great, everything's plugged into each other. But how do we use this? This is the first protocol we'll talk about. We'll just talk about the background of this one. We won't have to mess with the internet protocol or what we'll see later, TCP, to form our TCP IP. We won't talk in depth, in detail, but I want to give a high-level overview of how we're going to use these. So IP, the internet protocol, is how we're going to send messages over these cables. This is how information is routed through the internet. This is it's going to be redundant no matter how I word it. It's the protocol of the internet. It's literally the internet protocol. The physical cables and the internet protocol combined, that is the internet. Nothing else is the internet, including TCP. TCP is not the internet, but TCP is commonly used on the internet, but does not define the internet. So IPv4 and IPv6 are the ones that we're using now. If you want to read the official standard, there's way more information than you'd ever want right here. And the whole idea of the internet protocol is to give every device connected to the internet a unique IP address, and then tell the routers of the internet how to route based on that address. So the routers in the internet are going to get a packet for a specific address, and that router has to decide, how do I get this packet to its destination? How do I route this packet through the internet? So these packets, all the information sent through the internet is going to be formed in these packets, which are going to have a header containing the most important piece of information, the destination IP address. Where is this thing going? How does it, so the routers know how to route it. And then the payload, that's everything that we're going to care about. The payload is usually going to contain multiple other protocols. In this class, TCP and HTTP and HTTPS are going to be the other protocols that we're going to wrap in that packet. So if we have this address, a router has to decide how to route it. It's usually not reading the entire address. These addresses work with prefixes. So common prefixes are usually the same company. So for example, UB has a chunk of IP addresses where any IP address with the prefixes of that chunk, I guess Google's the example I have on the side, I'll switch that. Google has anything that starts with 172.217. Anything that starts with those two numbers is a Google IP address. A router's just going to read those first two numbers and know, oh, this is going to Google. I don't have to read the rest of the IP address. Just going to read that prefix and send it on its way over to Google. And then Google's going to read the last two numbers once it hits Google's network, and then Google can figure it out from there with its hardware, with its routers. There's a few different types of IP address. IPv4 is 4 numbers. This is like what we saw in the previous slide. 4 numbers ranging from 0 to 255, separated by dots commonly. The machines are going to read this just as a 32-bit integer, but we separate it by dots and change the numbers 0 to 255 just to make it more human readable. But a machine is just going to read this as a 32-bit integer. It's 32 bits, which means we can have about 4.3 billion devices connected to the internet. Sounds like a lot, but it's far from enough for our needs these days, for how large the internet has gotten. When the internet was first invented, when these protocols were first written up, or when IPv4, I guess, was first written up, that sounded like plenty, but as we all know, the internet became a big deal, and a lot of people connected to it. 4.3 billion is somewhat comparable to the number of people on the earth. Not everybody has an internet connection, sure. So maybe only 4.3 people are connected to the internet. I don't know the exact number actually off the top of my head. But a lot of us have multiple devices. Right now, I need 3 IP addresses for my 3 devices that I'm using right now. So we quickly run out of this once people have multiple devices connected to the internet. I have my Netflix, or not Netflix, Alexa at home too, some Internet of Things devices. Just for a single person, we need quite a few IP addresses. So we quickly ran out of IPv4 addresses. There was this big panic. It was quite a while ago now. It seems more recent than it was, probably 10 or 15 years ago, I'm guessing. There's this big panic. We're running out of IP addresses. We need to do something. So a bunch of great minds got together, came up with apparently IPv5, I don't know anything about, which they trashed. And then IPv6 was the one that stuck. IPv6, same idea, except 120 bits for each address, for each IP address. And this lets us represent a lot of different devices. We can get that many devices. So it's a lot, and I'm pretty confident that's going to be enough. I mean, they were a little naive when they said this would be enough. They said, we're never going to reach that. So I might sound naive, but I think that's always going to be enough. I don't think we'll ever need more IP addresses than that. Some of my basis on that is this number here is larger than the number of atoms in the universe. So even if every atom in the universe needed its own IP address, we still have plenty to spare here. Number of atoms in the universe, I think it's somewhere around 10, I'm not going to spitball that one, I'm going to get the number wrong. But it's comparable to the number of atoms in the universe. I think we'll be fine. Routers these days can handle IPv4 and v6. There was this big transition when IPv6 was first adopted. Only some routers could handle it, and we had to have IP tunneling and things like this. These days, I think all the hardware is updated that everything can speak v4 and v6. So routers on the internet have to handle both. A lot of the IP addresses we can still see IPv4, but usually especially when it's a server we're connecting to. But when it's a client, like I probably have a few IPv6 addresses here connecting to UB's network. When they run out of IPv4, they start handing out IPv6 or however they decide, and they'll give us IPv6s. An IP packet is going to be in this, the header is going to be in this format. This is directly from the standard for IPv4. So the question, if we're sending information over these cables, whether it be fiber or copper or Wi-Fi, whatever the actual physical layer is, how do we send information over this when we only have the ability to send high voltage, low voltage, or high light, low light, light and dark? We only can send binary information over these wires. How do we decide how to represent information? And that's what the IP protocol is going to define. So the very first bit that's sent, the very first either high or low that's sent, is going to be the first bit of the version of IP, and then the next 3 bits, that's the version of IP. Am I using IPv4 or v6? A bunch of stuff that I don't fully remember what it is. Again, this course is going to start with HTTP. I'm just doing this as background, so I don't remember everything exactly. Yeah.
Can I ask you a question about why can't we use MAC addresses? If we can use MAC addresses, you never have to worry
not gonna have an exact answer for you. I do know MAC addresses can be spoofed. Let me brainstorm a second. I think, so if I have a MAC address, how do you know where that machine is? Like I can have one MAC address here, and then if I take my laptop to California, how do you know where to route that packet? I believe that would be the big hang up on that one. Because the IP address tells physically, like when I'm here, UB's network gives me an IP address of theirs, so now they know how to reach me. When I go home, I'll get a new IP address. I'll be back to my Verizon IP address, and then the sites know where to route that. MAC address wouldn't be able to do that. Is my guess of why we wouldn't do that. And then, so after reading so many bits, we'll get to the source address and destination address. So now once this destination address is read, the router can figure out where to route this thing. But they're doing that based on when those bits were sent. So it's reading the binary to be able to tell, and in this specific format, to tell where that destination address is. So on both ends, both devices have to be speaking the same protocol, and just by putting things in the exact order that they appear here with the exact number of bits. And as long as they're both speaking IP, then they can know what to do and they can successfully route our packets. And this is where it can seem like there's magic in the internet. This is one part where we're going to start peeling back the magic. There's no magic. We just have physical wires connecting devices, a bunch of routers, and they're sending bits in this very specific order. And then with the total length and then the actual message below here, what you want to send, that's how they're getting information from one device to another device anywhere on the planet. It's just protocols, which is really just defining the order of the bits of the information we're going to send, and then physical wires plugging everything into each other. That's really how the internet itself works. And it does work only on IP addresses. There's no google.com and anything that I just said. One thing that we do use to make our lives easier as humans is DNS. This is where we actually have our domain names. So domain name, you register a domain name with a domain name server, a DNS, and then your browsers are hard-coded for the IP address for each DNS. Not hard-coded, you can change it. But you connect to that DNS with a request. The DNS says, hey, here's the IP address for that domain name, and then a request is sent to that IP address. The internet only knows IP addresses. We like to work with domain names, so we built this extra layer on top of that to be able to use the internet to find IP addresses based on domain name, and then we don't have to think about IP addresses, even though computers always use the IP address. And you can go to your favorite sites directly by their IP addresses if you'd like. Some sites, some servers don't allow that, but most of them will let you do that. And then we have these routers that are going to read the destination IP address of each packet, and then route that packet to its, what we call its next hop. A router's job is to look at it, read the packets, look at the destination IP address, usually just a prefix of it, and then send it to its next router in the internet. Just its next router. And that's it. These routers are highly optimized for speed, but not reliability. They are very simple. They're just scan destination IP address forward. And that's it. The big thing that's missing here, the big feature that you would want these routers to have, is there's no fail-safe. It forwards a packet. It never waits and says, hey, router, did you get that packet I sent you? That router might be offline. That router might be offline, the cables might be cut, there might be a power outage in that region, or any number of things. That router does not care. No routers on the internet care about that. They don't care whether that packet made it to its destination or not. It just has a queue of packets coming in, looks at the destination address, throws it wherever it's supposed to go to the next router, throws this to the next router, and that's it. Doesn't check for any reliability. This is where we get dropped packets. This is a reality of the internet. And this is something we'll talk about next time, is TCP is going to address this problem of dropped packets. And make it so it's not something we have to think about. Yeah, with that, I'll see everyone Wednesday.